This is the largest rocket in regular operation today. The Ariane 5 represents the evolution of a family of launchers that started when Europe's space industry was in its infancy. This massive launch vehicle is built all over Europe, but assembled here in the cathedral at the Ariane Group construction site at Les Mureaux. It is a robust design that has resulted in 85 completed launch missions in the last quarter of a century. But in the next 2 years, it is due to be replaced by the more versatile and competitive Ariane 6.
Six, 5, 4, 3, 2, 1, top. Allumage Vulcain, allumage des 2 EAP et décollage vers 244.
The Ariane 5 launcher shoots into space. Its rockets not only pushing its own weight in metal and fuel, but also a high-tech payload. The launch is the culmination of decades of development, experimentation and research in engineering and ballistics. The 2 lateral boosters weigh 227,000 metric tons each when full of fuel, the equivalent of more than 15 towers of Pisa. They are 30 meters tall. Each one provides 6,000 kilonewtons of thrust, 6,000 times the force of gravity, and pushes more than twice the weight of the launcher and its payload. This is just the beginning of the Ariane 5's voyage into space.
That's why rockets are dangerous, because they are, by nature, they are very explosives.
Reaction, which was found by Newton in 1687, okay, is you expel something behind you fast, and the faster you expel it and the heavier what you expel is, the more reaction you get.
The most exciting moment, and this is the reason why we are having that profession, is the first time you launch a new launcher, or the first time you launch a launcher on which you have had a key role in the design of it, or for my case this was in the change of the flight software, rebuilding the flight software of a launcher.
The Ariane rockets were developed in France, but draw on almost a century of experimentation and research worldwide. Europe's rocket scientists began with simple, unreliable machines. One of the founding fathers of modern rocketry, the Russian Konstantin Tsiolkovsky, discovered the propellant power of liquid hydrogen and oxygen. In 1914, the American Robert Goddard proposed multi-staged rockets, solid fuels, and the use of the Laval nozzle, narrowing at the waist to accelerate the hot gases to supersonic speeds. In Germany in the 1920s, Hermann Oberth studied rocketry and proposed that rockets could be used to explore interplanetary space. But when the Second World War broke out in 1939, all Germany's rocket science was put to building wonder weapons. Wernher von Braun led the rocket program based on the Pomeranian shoreline at Peenemünde. It did not change the course of the war, but it opened a new chapter in space exploration when Wernher von Braun moved to the United States under Operation Paperclip, while other top German scientists were taken to Russia. Wherever they were made, rockets were, at first, powered by extremely volatile propellants. One of the world's foremost aerospace journalists is Bernard Chabert from France.
In a rocket fuel, you have two components. You have the propellant and the oxidizer. The propellant can be kerosene, just like on the first stage of Apollo, for instance, and the oxidizer is something which helps burn. And chemically, when you have this mix between a very raw fuel, propellant, plus a very basic but nevertheless violent oxidizer, the more violent it is, the more powerful it becomes.
Engineers have learned from the many mistakes of the last century to produce the reliable, fine-tuned rocket engines of today.
Mechanically speaking, it's a nightmare. And then you bring them into a combustion chamber where they have to be precisely mixed, more precisely than any cocktail in a bar. It's really it's pure chemistry. You're working at the extreme of metal capabilities. You are going to really try to break something and stop just before it breaks. You have to gimbal the thrust, and this is done. It's just like cutting flowers. It's really something very precise, and it's almost a work of art in terms of guidance.
Russia's own rocket genius, Sergei Korolev, began the Soviet Union's own rocket program, developing first the Sputnik satellite, kicked into orbit by an R-7 rocket, and then the first manned spaceflight. By 1959, Russia had landed a vehicle on the moon and sent a satellite around it. Russia was winning the space race, and the United States had to respond.
The Russians built the number of R-7 Semyorka they made is absolutely staggering. It's tens of thousands, because they used it for military use as ICBM, and they used it to launch Gagarin. They launched the Sputnik with it, they launched Laika with it, and today we are launching, Europeans are launching Semyorkas from Kourou, because that rocket is is so dependable and so predictable and so easy to use that it's still in use today, and it's more than half a century away.
Outside the Soviet Union, only the United States had the ability to launch satellites. European nations came together to attempt to launch their own rocket, but it was a disaster.
British came with the Blue Streak missile, which was a strategic missile. The French came with Véronique, which was a small rocket, but which had evolved into technologically comparable rockets. And everybody came with its own little thing, and they stacked the thing together, and they called it Europa, and they brought it to Australia and pushed the button, and the thing exploded in billions of little pieces.
The French space agency, CNES, Centre National pour les Études Spatiales, is located in the heart of Paris, and Christophe Bonal is senior project manager. He has been involved with the Ariane project since the beginning.
We developed a satellite, brand new satellite, together with our German colleagues called Symphonie. This was in 1974. And so we had no means to launch Symphonie. And so we asked the Americans, could you please help us and launch our satellite? And they said, yes, okay, yes, sure, no problem, you're welcome. With one condition only: please don't make any commerce from this after. Just keep it experimental, and don't do any commercial activity out of this. And then we thought of it and said, no, oh, whoa, no, thank you. We'll do it on our own. And so this was a decision for the development of a brand new family of launcher.
The Americans, with their position regarding telecom satellites, created in Europe and more specifically in France, created a kind of reaction, and some of the French said we need to be independent in terms of launching capacity. We need to develop our own system, despite the fact that we've just missed the thing with the Europa experience, and that's how they got together. At the same time, they developed the idea of ESA.
The European Space Agency brought together the founding nations to develop an independent space capacity. However, Ariane 5 was still a long way away. In the 1970s, NASA developed the Space Shuttle, a reusable launch system that was designed to radically bring down the cost of launching satellites. It was an engineering masterpiece.
There was this old idea of an aircraft going so fast and so high that it would get into orbit, and it became the shuttle. But the thing is that I was there in Houston when they were launching the shuttle idea, and we had endless conferences about that, and people saying the shuttle is going to be a mix between the best of the rocket and the best of the aircraft. And the end result was that the shuttle was a fabulous mix between the worst of the rocket and the worst of the aircraft.
When they did the space shuttle, in their opinion, it was such a revolutionary machine, which should be able to fly every day, and for negligible cost, so cheap, just to use and so on and so on. And so they came and told us, but stop your Ariane 5, it's useless. Just come and work with us in the space shuttle. And we said, sorry, but we like our autonomy, and okay, our launcher may be conventional, but we think it has some future. It paved the way for the huge success of Ariane that we still have today.
The Europeans decided that there was a market. What does the market want? What does the market need? And they found out that everybody in the world was waiting for the age of telecommunications to arrive. And so they developed the first model of Ariane, and they evolved it into different new systems, which were only beefed up versions of the basic philosophy, up to Ariane 4, which was probably the most extraordinary of them all in terms of delivery, in terms of cost per kilo to orbit.
Demand for the ability to launch satellites into space was literally skyrocketing. The Ariane family of launchers evolved throughout the 1980s, together with the telecommunications and observation satellite markets. By 1990, the Ariane 5 was well on its way to being the workhorse of commercial rocketry. This is the so-called cathedral, where the Ariane launchers are assembled. It is here that the mystery of spaceflight becomes solid engineering. Hervé Gilbert is the chief technical officer of the company that actually builds the rocket, Ariane Group. He is here to oversee an event that is rarely filmed: a central cryogenic stage being loaded into a container for transport to the launch pad at Kourou in French Guiana.
We are in our final assembly line in Europe. This is the building named Building 60 in Les Mureaux, where we assemble the main cryogenic stage of our Ariane 5 rocket. This stage, you can see it behind me. We are very lucky today because we are moving one stage from the building here towards Guyana, so it will be put horizontally in the coming minutes. This stage from here is shipped to Kourou, and there in Kourou we finalize the assembly with the other stages that will join it and constitute the final launcher.
No less than 4 cryogenic main stages of the Ariane rocket are under assembly here today, and the industrial work involves riveting and subsequent cleaning of the rocket bodies, followed by the insertion of the engines and piping, fuel tanks and turbopumps that turn these massive steel cylinders into rockets. It can be a noisy process. The key parts of the central stage that is ready for delivery are enveloped by purple covers, and each moving part is blocked by pins that hold them in place. The rocket will not be launched until every single purple element, cover and pin has been removed and visually accounted for. The blue bracket over the engine is to protect it from inadvertent breakage during transport. The Ariane rocket system is incredibly complex and is made up of 5 major parts, each of which is built separately and assembled into a final launch vehicle only when they reach the launch site in distant Kourou, in French Guiana. It is a production process that involves millimetric precision and deliveries to the construction site under extremely tight schedules.
So if we look at the rocket as a whole, this is a matter, at the time of liftoff, this is a matter of 780 tons, of which the 2 boosters, there are 230 tons of propellant in each of them.
You have 2 large solid boosters here, which are used to provide a very large thrust, typically 7,000 kilonewton or 700 tons for the older one. So they burn during 2 minutes and they expel 2 tons per second. So imagine we are expelling the equivalent of 2 cars through a hole which is large like this, 2 per second, okay, 2 tons per second, at velocity of 20,000 kilometers an hour per hour. So this is producing a huge thrust. This helps us really lifting from ground, getting out of the atmosphere.
If we take now the central core is composed of the main cryogenic stage, an upper cryogenic stage, and the upper part. The main cryogenic stage weighs, let's say, roughly 190 tons, of which 175 tons of propellant, 25 tons of liquid hydrogen, and 150 tons of liquid oxygen. So this is the lower part, but the bigger part of the launcher.
Of all the parts of the Ariane 5 rocket, it is the lateral boosters that give it the power to get out of the Earth's gravity and through the lower parts of the atmosphere. They are called the EAP. The boosters are the most vital element of the rocket to get it onto the right trajectory to orbit. The choice of solid fuel gives it the maximum power in the shortest space of time. The solid propellant's job is to push the rocket into the high atmosphere. But despite its apparent robustness, the rocket is fragile. The rockets are programmed to provide just the right amount of thrust at the right time.
In the solid boosters, we're using the oxidizer and the fuel, mix them together in a solid form. For the oxidizer, we're using ammonia perchlorate as the oxidizer, and we're using aluminum pulverant, really in a very, very tiny powder as the fuel, as the reducer. And so the reaction between the 2 of them generate the very high temperature, very high pressure, which is used for the propulsion.
Engineers have discovered ways of providing exactly the right power at the right time by modeling the way the propellant is inserted into the booster.
The very first thing that we ask to these boosters is to have a very high thrust, to get out of Kourou as fast as possible. What we do is that instead of just a pure cylindrical canal, we have a kind of star shape. Okay, so we increase artificially the surface, which is in fire, okay? And so this gives us a higher mass flow, so a higher thrust.
The solid propellant in the lateral boosters is extremely fast-burning and volatile. It provides the power to get out of the atmosphere, but also makes up 90% of the rocket's weight.
Once this star is completely burnt, then we have less surface, and so the thrust is going down. And that's very important because this is the most critical part of the flight, which we call the maximum dynamic pressure, which is the moment of the flight where the aerodynamic stresses on the launcher are the maximum. Then I burn my cylinder. So as I increase through time the size of the canal, I increase slightly the surface of the cylinder, so the thrust increases all the way until I have nothing left to burn.
As the booster's propellant burns in contact with an ever-increasing surface, so it produces more power. Starting from the top, the star-shaped section of the propellant allows it to burn fast. But when this has been exhausted, the burn slows down until, as the fuel burns and the exposed surface increases, it begins producing more and more power, the final kick to get the rocket out of the atmosphere. The two solid fuel boosters are attached to the main rocket via solid brackets that hold them in place to ensure the power is perfectly controlled. However, the main force applied to the main cryogenic stage is at the shoulders.
One could believe that the two boosters are attached to the main core via the three rods, twice three rods we have in the bottom part of the launcher. In fact, they are not bearing at all the loads generated by the thrust of the two boosters. What we do is that we link actually the main core and the boosters through the head of the boosters. In fact, we push the main core and the main cryogenic stage that you can see behind me, in fact, is not designed to sustain the very high loads that would come from the boosters through the rear part, but it is simply hanging between the two boosters. This is our little secret, let's say.
All the thrust goes through this here. Here we have a kind of joint, spherical joint, where all the thrust is passed. So we have a cup and a sphere, and so this takes out all the thrust in all three directions. But then, how do we prevent this kind of movement? For this, we have three struts at the bottom of the launcher, which prevents the lateral movement like this. So all the thrust goes through the front joint, and the lateral movement, are stopped by the three struts that we have at the bottom of the stage.
So here we have the shoulders, what I name the shoulders, which are between the one booster and the main core stage. And through this very little metallic part, we have 600 tons of loads which are taken over and absorbed in order to lift the main cryogenic stage. The two boosters are bearing, pulling the main cryogenic stage through this very, very little metallic part.
The booster is equipped with an orientable nozzle made of carbon fiber to withstand the massive temperatures and pressures developed at its mouth.
When we design the launcher, as we are doing for Ariane 6 today, we take care to have a capacity which is in the range of 5 to 7 degrees, not more than that, for all the nozzles, for the boosters and for the main cryogenic stage. Practically speaking, in flight, it is very, very seldom the situations where we have more than 2.5 degrees of gimbaling are very seldom. But we size it for 7 degrees most of the time.
The main body of the Ariane is made up of a huge cryogenic engine. The Ariane 5's engine is called the Vulcain, Vulcan, the god of fire, in French. Although the principle is very simple, the actual workings of the rocket engine are extremely complex. The cryogenic engine used on the Ariane rocket is a formidable tool for getting satellites into space. Its workings are amazingly complex.
The cryogenic engine is a fantastic machine. This starts with a small gas generator which takes liquid oxygen and liquid hydrogen from the tanks on the launcher in order to generate a flame, gases which are exhausted at a very high speed, to put in rotation two turbines, the liquid oxygen turbopump and the liquid hydrogen turbopump. These two turbopumps are also fed with liquid hydrogen and liquid oxygen, and they push that amount of fluid into a thrust chamber, into an injection plate, which is the entry of a thrust chamber.
We are pumping hydrogen, so the liquid hydrogen has some specificities. First of all, it's so lightweight. It is 14 times less dense than water. So you have the impression of pumping air. So for this you need to have very, very high performance turbopumps going very fast in order to pump as much as possible. So for instance, the turbopump of the Vulcan engine on the hydrogen side is something of the size of a microwave oven, if you want, and it has the same energy as two TGV trains, two fast trains, so it's very, very, very impressive. So you have one turbopump for hydrogen, one turbopump for oxygen, and so from the outlet of those you inject into the combustion chamber.
The propellants are composed of a highly combustible element, in this case, hydrogen and an oxidizer that causes the combustion, oxygen. In order to store them in liquid form, they need to be frozen to below -200 degrees centigrade. The two liquid gases, however, will not mix by themselves. They need to be pushed together through pipes and injected into the combustion chamber at exactly the right speed. This is the job of the turbopumps. However, these are actioned using some of the energy produced by the combustion. So to get them working, liquid helium is pumped from these spherical tanks into the main fuel tanks to push the oxygen and hydrogen through the turbopumps into the combustion chamber to ignite. Calibrating the pressures is extremely complex. Bringing all the pieces together to build an Ariane 5 is a remarkably complex operation. The main stage is completed here in Les Mureaux, but the Vulcan engine is built in Vernon in Normandy, while the boosters are made in Bordeaux, and the third stage in Bremen, Germany. The turbopumps for the engines are made in Italy. Bringing all this material together and making sure they all fit is a complex operation and requires months of checks and tests.
Parts are coming from Germany, MT Aerospace in Augsburg for the upper skirt. Parts are coming from Les Mureaux here. The company which is just beside me here is delivering the tanks together. Then we have below the tank we have a thrust frame which is coming from Netherlands, and then the engine, the Vulcan 2 engine, is coming from Vernon in France. Most of the time we take in this final assembly line is with checks of tightness, checks of electric continuity, electric isolation, and so on. This takes 9 months, whereas the mechanical assembly is a matter maybe of 1 week, not more than 1 week.
We use our third stage, which is here, which is also a cryotechnic stage. Hydrogen, oxygen, liquid. We have 15 tons of them, propelled with an engine which is called the HM7B, okay, which is and so this one guarantees it works during for 20 minutes roughly, and gets all the way to orbit. And so once it reaches the proper orbit, then it is automatically cut.
While the main parts are made in France and Germany, with the payload fairing coming from Switzerland, the final rocket is assembled on the launch site at Kourou in French Guiana, where the solid fuel is mixed and molded for insertion into the boosters and, as a very last stage, the cryogenic liquid fuels are loaded into the central and second stages. Kourou, French Guiana, is a tropical paradise. But most people come here not for the beaches, but because of its latitude. This is an ideal place, close to the equator, to launch a payload into geosynchronous orbit. Here, vital activities complete the production process of the Ariane 5 rocket. This is where the boosters are filled with solid fuel, and where the liquid gases, hydrogen, oxygen, and helium, are loaded into the tanks. The ground infrastructures are massive, and the launch pad is designed to survive the huge thrust provided by the rockets and the cryogenic engines. This is where the weather is monitored, the winds especially, that can cause a mission to be delayed or even aborted. This is where the control room follows every second of pre-flight activity, and where the computers that control the flight are located. It is a massive infrastructure owned and run by the French space agency CNES.
5, 4, 3, 2, 1, top. Allumage Vulcain, allumage des deux EAP et décollage VA244.
As the rocket hurtles through the air, out to sea at first and then up into the stratosphere and into space, the fuels in the boosters and the first stage burn up. The boosters are jettisoned and fall into the ocean. They are reusable and are recovered in the Atlantic, while the first stage accompanies the payload into space and then falls back to Earth once empty and burns in the atmosphere. The second stage kicks into operation, taking the payload fairing to the height required. Once the rocket has been launched, the most complex part of the mission is yet to come: controlling the rocket and pushing it onto the right ascent path.
A launcher such as this one is very unstable. What means unstable? It's just like a pencil on top of your finger, and you really need to try to keep it vertical. It's very complex. You need to move very fast. Here, it's even faster. You need to react every 70 milliseconds. Otherwise, you lose it. Otherwise, you don't control it. It flips back, and then it's destroyed. And so what we need to do is to control it real time, very, very fast. So it has to be done on board.
At any point in time during the trajectory, the onboard computer is evaluating the current position and the trajectory that should be followed. This is guidance. Navigation is providing the instantaneous location. The most fascinating part probably is the control of it. So by steering the orientation of the nozzles, so steering the orientation of thrust, and getting the counter reaction of the body which accelerates, we take care, in fact, to put it on the trajectory that has been determined by the guidance, knowing that by nature such a launcher is fundamentally unstable.
There are different kinds of orbit, and since the Ariane is able to carry 2 satellites, a dual payload, the final stage with the payload fairing is sometimes required to move from one orbit to the next.
So on Ariane 5 we launch typically 2 satellites, one big one which is in the range of 6 tons in the upper position on the launcher. Then there is an intermediate structure which looks like a bell. So the upper one is put on the bell, and there is a smaller one, 3 tons and a half on the lower position under the bell. So this is the performance of Ariane 5, 10 tons roughly for the geosynchronous transfer orbit. Okay. Ariane 6 will be a little bit better by 1 ton, typically 1 ton more, which will be allocated both to the smaller one and to the bigger one.
Today, the average size of a satellite, of a GEO satellite, is 5 tons at launch. So 2 of them, we need 10 tons. And so this dictated the performance of Ariane 5. We set a record, a world record, very recently with 6.3 tons on one satellite. And we have some satellites at up to 8 tons.
This is the most delicate phase of the mission. It is the moment when the value of an object launched into space comes into its own. The make or break moment of the launch comes when the final stage pushes the payload into its final orbit. The last stage, which holds the payload fairing, is powered by a highly flammable and toxic fuel called MMH hydrazine.
Where we very often aim at is what we call low Earth orbit. So low Earth orbit are roughly up to 2,000 kilometer altitude. This is very used for all the observation missions. This is one of the key market, all the low Earth orbit for the observation, for environment, for meteorology, and so on. Then if we move on, we have at roughly 20,000 kilometers from Earth. Here we have the GPS satellites, the Galileo, and their equivalent. The most useful orbit is the GEO, geostationary Earth orbit. Geostationary, it means it's an orbit where a satellite, when placed there, is always seen as fixed from any observer from the ground. That's 2/3 of the commercial market today.
Apart from launching thermonuclear weapons, the only goal of rocket building is to launch satellites and modules for the International Space Station. Communications satellites may cost millions to make, but over a service life of decades, and with the spread of radio telephony, they will pay for themselves many times over. In proportion, the cost of launching is minimal, and that cost is further reduced by economies of scale. Ariane Group's future depends on the evolution of the satellite industry. While Ariane 5 was initially developed by the European Space Agency under the technical leadership of the French Space Agency, CNES, the next European rocket is being developed directly by the constructor, Ariane Group.
There was a decision that was made by the European member states, the European governments, 4 years ago, by which we decided to group under one single umbrella, one single industrialist, the role of lead system integrator in production, which means the architect of the launcher during development and design of the launcher, and the engine manufacturers, so teams from Airbus for the first part and from Safran Group were put together in one single company, which is our company now, Ariane Group, and the decision was made that this company should be the prime contractor and the architect of the launcher.
Competition in the marketplace has picked up with the arrival of private constructors. The first launch of the Falcon Heavy in February 2018 seemed to be a turning point in Elon Musk's ability to deliver heavy satellites into space. Ariane Group has chosen a different path for the time being.
We have changed some little but big things on Ariane 6 with respect to Ariane 5. The boosters are smaller on Ariane 6 than on Ariane 5, so this is a matter of 147 tons of propellant per booster on Ariane 6. So 2 big boosters for Ariane 5 and 2 or 4 smaller boosters for Ariane 6, which gives modularity and which gives us the opportunity to launch small payloads at low altitude, low Earth orbits, or bigger payloads, even slightly bigger than the ones of Ariane 5 today, when we have 4 boosters on high altitude orbits.
Being able to modulate the weight and power of the launcher will mean that Ariane 6 will be offering a more flexible launch service. Many smaller satellites or fewer large satellites, 2 lateral boosters or 4. And above all, the final stage can be reused to position satellites in different orbits. The cryogenic engine will be improved, although the basic structure will remain the same. Construction of the rocket will be more streamlined too, and the thousands of rivets holding together the cylindrical segments of the rocket will be replaced by a new form of welding.
Another aspect is, another example I have in mind, is about the way we weld the panels that constitute the tanks. So we had quite old technique which is used on Ariane 5, because Ariane 5 has been designed in the 90s, even a little bit before the 90s. So all the welding techniques are replaced now by a safer one, a more secure one, which is named friction stir welding, and which works simply by melting the two parts you want to join. You melt the interface between them, and then they naturally stick to each other without any defect and discontinuity in the material.
Friction stir welding uses friction to melt two surfaces to weld together, and as they melt, they are pushed together to form a single surface. It is another new manufacturing technique that increases robustness and lowers cost.
What we have been doing, what we are preparing, on Ariane 6, is new ways of manufacturing. Additive manufacturing is really paying off when we are speaking of propulsion parts, parts of turbopumps, parts of gas generators on board of the engines, building these parts via additive manufacturing, which is 3D printing. By doing that, we save a lot of times. We save months in the production of these parts, a lot of energy, a lot of power supply. So there are lots of savings done here, but we keep the same material as before. We just manufacture the part in a totally different manner.
The Les Mureaux plant has been redesigned, with an entirely new factory built alongside the cathedral. The Ariane 6 will be built horizontally, allowing easier access for workers. Europe deploys its own navigation system, Galileo, using the old Ariane 5 workhorse that has paved the way for European access to the growing space economy. As the rocket, with Galileo aboard, hurtles into space, powered by its two lateral boosters and the cryogenic Vulcan engine, its mission is to complete the European-owned and managed navigation and observation system. In the future, exploiting space will take not bigger rockets, but more versatility, and Ariane 6 and other rockets such as the Italian Vega attempt to stay competitive on the market.
So the first measure we have taken when observing this drastic reduction of the cost of launch service that Elon Musk has been able to do has been to develop the Ariane 6 launcher. More or less twice cheaper than Ariane 5, with a higher capacity in orbit, a higher versatility in its missions. It will be capable of many types of missions in orbit, many types of orbits, whereas Ariane 5 ECA, our workhorse today, is only capable of one type of orbits.
Born out of the French and German drive to create an independent European space launcher, Ariane 5 and 6 is a collaboration between Ariane Group, Ariane Space, CNES, and industries all over Europe. Hervé Gilbert has lived the life of the space engineer for a quarter of a century. He has had some exciting moments.
You have simulated many things. You rely on your simulators. The particularity of our business is that we never fly for tests. We fly for going to space at the first time. So the reality and the truth of everything you have modeled before flying, you will discover it during the flight, the qualification flight of your launcher. So these are fantastic moments for us, and we are really looking forward to having these moments together for Ariane 6 in 2020.
The sun sets over Kourou, French Guiana. This equatorial country, still under French authority, offers the perfect place of launch for heavy loads into space. Hundreds of space engineers and technicians work here to make this international effort successful. Another Ariane 5 is ready for launch. Another space adventure about to begin.
4, 3, 2, 1, top. Allumage Vulcain. Allumage UAP, décollage. Tous les paramètres à bord sont normaux.